Lasson. Lasson is an associate professor at College of Computing at GeorgiaTech, and he has done amazing work in the area of AI and machine learning. And more recently, he has been doing his sabbatical at M Financial, and in particular looking at how to use deep learning for security applications. So let's welcome.
Okay, thank you for the introduction. Thanks for everyone for coming. And it's my honor to speak here in this security and AI community. About today is going to be how do you actually deploy some kind of deep learning technology over various type of complex network, especially there are some kind of security problem involved. So let me just give you some examples within the Alibaba. So Ant Financial is a subsidiary of Alibaba. So the mission of Alibaba is to connect buyer and seller. It doesn't matter it's going to be big kind of shops or small shops or you are rich people or poor people. You can actually go to this platform and buy things in this platform. So along the years, Alibaba has significantly expanded its sort of business to touch upon various areas such as social networks and entertainments and even traveling. Okay. So you can imagine that along the process, that there's many financial transactions going on in this platform. So playing the key roles in this Alibaba ecosystem is going to be M Financial. So it has this mobile app which you install in your mobile phone. Essentially, you can use that account to pay for all kinds of stuff. You can also pay things offline. Okay. So in some sense, that many data. Many different type of data in M Financial is going to be a complex network. You can imagine that this M Financial is actually having lots of data connecting various type of entities. It can be user accounts in this platform. It can be shops in this platform. It can be even some of the device ID or IP address, Wi-Fi access point, and GPS location, things like this. Okay, so because every transaction when it has happened, you will have this information recorded in the database, essentially. And because there's a diverse range of people using this platform and a huge variety of shops in this platform, there are many different type of fraudulent behavior in this, happening in this platform. You want to detect it. And then typically all this detection problem will be something on the detection problem on the network. Let me give you one example. This is one example about just fake account detection. So when someone registers an account, and then it might not be just a normal account. It might be an account registered by some hacker or some fraudster. And then in the normal kind of payments, this account is not going to be active. But when there's a promotion or something like this, so this fraudulent account might just be active and come to get some coupon or something and disrupt the normal kind of promotion activity. Okay. So in this kind of Alipay platform, so actually every month there are millions of accounts being created. And many of them are fraudulent accounts, and you want to detect it. You can think about in this case, each one is a node, can be an account. And then when the account being created, it's associated with some kind of device ID. And this account can be logged in using different device ID. You can think about all these accounts and the device ID or even Wi-Fi access point that are connecting all these entities together. So in this network, some of these accounts are going to be fraudulent accounts, some are good accounts. And you want to actually make a prediction or detection of these fraudulent accounts as early as possible. So the approach I'm going to talk about later, Structure2vec deep learning, currently actually being deployed in the system online, is going to lead to big improvements in terms of the detection accuracy. Okay. So this is the second application in Alipay. So in this case, there's some kind of behavior in this system called cash out behavior. So essentially, Alipay will also offer loans to people, microloans to people, right, based on their spending history. So these microloans are offered in a credit kind of format. So you can use this credit to buy some stuff in these Alibaba online shops, but you cannot get cash, right? But some people would like to cash out, okay? Turn these credit into cashes. So then there's some kind of shops, they are so special. They will somehow return the cash to this account user. For instance, this account user is getting $1,000 credit. And then he's paying these shops $1,000, but these shops are somehow via some route, some path is returning back only $800 in cash. Okay, this account owner is losing, in some sense, $200. There's no way for him to pay back the loan, and that increases the overall risk of people not paying back the loan. Okay, so you want to detect either those shops which allows these kind of cash out behavior, or you want to detect individual transaction which is cash out behavior. Okay. So again, you can think about in this network, and then the account are connected to shops, and then people are transferring money to other people, and the shops may also have transaction between them. And this kind of cash out behavior is hidden in a very complicated network. Some of the nodes in the network, or some of the edge in the network may be fraudulent kind of behavior, but some are not. Okay, so you want to figure out which one is the fraudulent shop or which one is the fraudulent transaction. Okay, as early as possible. So again, we have deployed the Structure2vec approach on this type of transaction network. And it's working much better than the existing approach, and now it's also online. So just to give you some idea of the scale of the problem, in this network, every day there are millions of transactions being carried out. And this Structure2vec approach is able to detect thousands of more of these cash out behavior. Each one is quite kind of fraudulent cash out behavior. It's going to involve thousands of dollars. Okay, so overall, like every day, this new algorithm is blocking millions of dollars of this kind of cash out behavior. Really a huge amount of money involved. So these are two examples where you want to actually do fraudulent detection over the networks. So there are many, many other problems you can imagine depending on the type of business you have. For instance, there may be fraudulent for insurance problems. Actually, M Financial also have problem of estimated the probability default, whether this guy is going to pay back the loan or not, based on his connectivity, things like this. So there's many of these type of problems. So actually, for all these problems, there's a fundamental challenge behind it. So previously, when we do machine learning AI system, very often the input is going to be a vector, right, of features. And then you just build machine learning model on top of this vector of features, and then you make predictions based on that model. So the difficulty or challenge in the network case is the data are input as some kind of combinatorial structure, right? It's not vector format. It's a graph, and every node is connected to every other nodes, and you might have different type of nodes, different type of edges. You might also have some features attached to each one's node. So it makes the design of these machine learning systems very, very challenging. Another source of information that is very important in these financial transaction network is going to be temporal information. So every transaction is happening in a particular point in time. So sometimes this cash out behavior, it is called cash out behavior because there's a temporal, forward loop in this money flow. Okay. So if the temporal information is wrong, then it is not a cash out behavior. So you need to take into account both the network structure and the temporal information to design some kind of machine learning system. Traditionally, before the deep learning, machine learning expert has to think about very hard what kind of feature to use. For instance, you need to take all these base feature, or in this case, even the network connectivity information, and think about how do you combine these all different type of features in order to first, and then feed it to some machine learning algorithm for downstream applications. So the fundamental question is how do you actually learn some representations from this network and then from all this temporal information, and then build some machine learning model on top of it. So the Structure2vec approach I'm going to talk about today is about learning some kind of features from network, heterogeneous network, complex networks, and also taking into account temporal information, right? So what is Structure2vec? Let me just give you the most simple version of this algorithm, okay? So this algorithm is actually an iterative algorithm, okay? So it's going to learn, for instance, a vector representation of each one is node in the network. And then later on, I will have a version that you can actually learn some representation for the edge as well. So, but here, the simplest one is learning some vector representation for each one is node. Hopefully, these feature, so for instance, a three-dimensional feature, three numbers, okay? Just for instance, but in practice, you use hundreds of dimensions. So it can capture both topological information, how these nodes are connected to the other nodes in the network. Also capture some additional information in these networks, such as node attributes. For instance, you can think about all these nodes, H1, H2, H3, up to H6. are going to be some kind of accounts in this Alibaba platform, right? Alipay account. And then each one of these nodes may have some original raw attributes. For instance, when this guy registered a particular account, he might enter the province, the location, right? And maybe the income and age, things like this. Okay, some raw feature. Okay, X. So what you want to do is hopefully these three numbers, these three-dimensional embedding can capture both how these particular nodes are connected to the rest of the world, and also take into account this raw feature X there. So this algorithm is going to compute this representation or embedding in an iterative fashion. So it's going to initialize each one of this node as some zero embedding, okay? And then it's going to update this embedding according to the network structure. For instance, if I want to update the embedding for node 1 over there, H1 there, so I'm going to actually have its neighbor, in this case, H2, 5, and 6, okay, sending some message to H1. And then and this node H1 is going to aggregate this message sent by the neighbors together with its raw feature and update in a nonlinear way. So this particular, I'm giving an example for the particular update. So in this particular update, you can see that this node J is actually just taking all these embeddings sent from the neighbors and do a summation, okay? J summation over J, which are neighbors of the node I. And then once you finish the summation, that's called pooling operation in the deep learning terminology. And then you apply transformation W2. And then the raw feature in hanging in this particular node Xi is going to also be transformed by W1. After you merge these two sources of information, you push these aggregate information through one nonlinear transformation, sigma there, right? So you can think about these update for the embedding for this particular node is going to be one-layer neural nets. And this one-layer neural nets is going to be parameterized by this parameter W1, W2. And this parameter W1, W2 are not going to be fixed beforehand. It's going to be learned. Okay, it's going to learn later on based on the prediction tasks you're going to have. So this operation, which are parameterized by W1, W2, is going to be applied to every one of these nodes in the network. So the difference between different nodes are the neighborhood structure and the corresponding node feature. But the parameter W1, W2 are shared across the network. Okay. Hopefully you want to learn a template. Okay. Operation, update operation, applied to every one of these nodes in the network, and in the end, learn some kind of vector representation mu capital T for each one of this node. Okay. So for instance, after one update, these feature embedding H1 is going to change like this. And you are also going to carry out the update for everyone in this node in the network. So once you finish one round, one sweep across the entire network, now the embedding has changed a little bit. Initially, the information are mostly coming from the corresponding node embedding X, right? Node feature X. But after a few iterations, after T iterations, the information is going to propagate through the network. And then the embedding is going to incorporate information from neighbors farther and farther away. Okay? If you iterate T times, effectively you are incorporating information from neighborhood of T hops away. Okay? This is the sort of intuition behind it. Okay? So once you finish T5 iteration, right? So this update are parameterized by this W1, W2. It's not fixed beforehand. But once you fix one of these parameter W1, W2, you're going to get some kind of embedding if you iterate T times. So now, once you finish the iteration, you have some vector representation each one to know. Now, if you want to do classification problems for individual node, you're going to take these embedding and connect it to some kind of logistic regression kind of, for instance, a model for the prediction for individual node. So depending on your application, if you want to make prediction for individual node, you're going to take the embedding for individual node and connect it to some kind of classification model. If you want to make prediction for a transaction, an edge here, so you're going to take the pair of nodes, which are two ends of the edge, and then define some kind of prediction model, for instance, logistic regression for that. Sometimes we also want to classify the entire subgraph or a small community. And then we can actually take all these nodes involved in that small community and do a pooling in the end, do an average in the end, and define a classification model in the end. So later on, I will show you some examples using this supervised learning approach. And I also talk about one example. Actually, you can use reinforcement learning to change some kind of models based on this embedding. So essentially, the goal of this embedding is to try to capture both topological information and then also some raw feature in the node, sometimes even the edges, and then come up with some number, okay? Okay, and then let's just come back to this example I mentioned earlier. And in this particular example, the network you're using is containing two types of nodes. One type of node is going to be these accounts, Alipay account. The second type of node is going to be device ID. And some people might log in multiple devices, right? And some of the nodes, you might already identify it as a good, or identify it as a bad, okay? And then from some feedback later on. So what you want to do is for some of this new account, you don't know about it. You want to make a prediction. So essentially, what you're going to do is you're going to essentially take these Structure2vec algorithm I showed you earlier. Okay, this propagation algorithm, which update recursively on the network and extract some of these features. For each one is a device, and each one is account. And then you can actually then connect this embedding to build some classification model for the node. So for this problem, we have compared to some of the previous kind of best algorithm deployed in the company. And the key figure to look at is going to be this precision recall curve. So recall means that you want to discover all these junk accounts, right? Ideally, you want to do it in 100%. Right? And then precision means that you want to disturb as few normal accounts as possible. You want the precision to be 100%, okay? And then such that every one of these accounts you detected, flagging as a fake is real fake account. Because you're going to shut down those accounts. You don't want to disturb any of these normal users. So this Structure2vec approach, which is going to be the red curve there, so it's maintaining a pretty high precision across the entire range of a recall. For instance, if you look at this recall, 0.5, the previous best approach they deployed is something called node-to-vector based on unsupervised learning of features. It's going to have something like a 70% precision. So, but this Structure2vec can go to 99% precision in this case. And very quickly, they take this approach and deploy it online to actually work on these fake account detection. So it's running every day nowadays. So just to give you a little bit more intuition, why do you need this network and to get a better results for this fraudulent account detection? We actually have a look at some of these lower level data. So look at this data in two kind of dimensions. One is look at something we call a device aggregation. So in the top two panel, right? So on the left side is going to be the behavior for normal account. And then you see on the axis is something called device ID, okay? And then the y-axis is going to be account ID. So these accounts are going to log in different devices. For the normal behavior, you sort of see that matrix there is more sparse, okay? And then that means that these accounts are going to sort of randomly log into some of the devices. But for these fraudulent accounts, you will actually see some kind of cluster behavior, especially on the towards the right-hand side. Some of the devices are used for logging for many of the accounts, okay? So this is some signature when you consider the network topology point of view, okay? So the second dimension is the account activity by itself. This account activity is like the node feature itself, right? The account itself, you can compute a node feature, how frequent it's logging in, and when it's logging, what kind of thing it's doing, right? So that's the X handling from each one of these nodes. So essentially what we are looking at in this case is the time in hours, and then in some sense, every time it's logging doing something, it's going to have some dots. And the y-axis is again going to be account ID. So for normal accounts, you sort of see longer duration of activity, okay? So some of the accounts only have activity here because it's newly created, okay? But for this normal account, you see more activity for each one is account. But for this fraudulent account, in some sense, if you look at the timeline, so each one is account, well, after it's registered, the activity are more sparse. So in some sense, there are two sources of information. which helps you to make decision. One is the connectivity information, how these accounts are being connected to these device, right? These are topological information. And then activity information is about the account itself, right? So you aggregate these two sources of information. This Structure2vec approach, while this iterative process is actually capturing these two types of information. That's why it's boosting the existing approach by a lot, okay? So this is the first example. The second example is going to be the example Dong-Song just mentioned about cross-platform code similarity detection. So in this case, the code, we are going to actually represent the code, each piece of code, as a graph, especially these control flow graphs. And then, so on the right-hand side, it's a particular function, yeah, a particular piece of code. And then each block is going to correspond to some small operation. And then when you see branches, it's some kind of checking condition. You might call different sub-function, for instance. And then based on this graph, actually, we can first do some feature extraction and get these more abstract representation on the upper right corner. So that one you can think about the numbers on each one of these block is going to be those node feature, okay? This node feature. And then this structure is going to be our graph. Each one is function is going to have a corresponding graph, okay? So then the question is, if I give you many of these code, and each one of these code is going to represent it as a graph, and then I want to learn some vector representation for each one of these graph, such that later on I can do very efficient and accurate search, yeah, to find similar graph or find some kind of malicious, for instance, kind of functions, okay? So the key question again is going to be learning some representation. So remember that the Structure2vec, while this iterative process, it can actually give you some kind of embedding for each one of this node. Now you want to classify in some sense, or want to represent the entire graph. You will actually do some kind of pooling over the entire graph. Okay. So so another question in this case is, in some sense, you need to learn these parameters in this embedding approach, right? So this update operator in this embedding is parameterized. You need to learn it. So we set out the new way to learn these parameters. So essentially, our assumption is for the same function, it can be compiled in different platforms. And the binary can be slightly different. You want to learn some representation of embedding which somehow is invariant across different platforms. You want the same function, even if it's in different platform, it's going to be similar, okay? So you want to learn representation. You don't want your embedding or representation to be affected by the platform. So we set up the problem in this way. So for each one, for instance, we are going to train these parameter always with a pair of network, okay? Always picking pairs of network or pairs of functions, okay? So these, each one is a function represented as the code graph is going to be computed the embedding using the parameter, okay? And then if these two functions, G1 and G2, yeah, represented as a graph, they are the same function, but across different platform. We want them to be similar, okay? Their label is 1. This pair has a label 1. If G1 and G2 are different functions, they might be in the same platform, across platform, they should be dissimilar. This representation learning should be dissimilar. So we give it a label -1. So in some sense, we have these so-called CMEs network or twin networks for extracting features, always comparing a pair of network. And then use that to set up the objective function to chain the parameters in this graph embedding approach. So this is we have many other results in the paper, but this one is just comparing after you finish learning these representation, and then use it to retrieve. Yeah, if you are provided with a piece of code, maybe compiled in iPhone, and then you want to retrieve similar functions in the in the database. You may compile it using other platforms such as Android. So you want this actually this curve to be on the top. Okay. So in this case, you look at a false positive rate, true positive rate. You want the curve to be towards the upper left corner. Okay. So we compare to some of these previous state of art, also for the same problem. Again, it leads to big improvement. So just to give you some idea of what has been done in the previous work, is mostly designing, hand design some features to compare graphs. So for this new approach, you are essentially learning a way to compare graphs. And these learning are parameterized using deep learning approach, okay? So you gain big improvement as well, okay? So, so I just explained to you this most basic version of graph embedding. So actually there are many other related updates. So all these updates or graph embedding approach, sort of they are inspired by some kind of message propagation algorithm, typically used in something called the graphical model approach in machine learning. So you might be very familiar with deep learning model essentially is some kind of nonlinear function mapping approach, either taking some image as input or sequence as input, output some classification or regression. And then there's a big class of algorithm machine learning called graphical models. It helps you model the dependency structure among many connected entities. And there's a principle, the system for reasoning about one thing happening in one part of the network, what could happen in the other part of the network. So these Structure2vec, in some sense, is merging together these two sorts of idea, okay? Make these graphical model inference becoming some kind of deep learning architecture. So based on this thinking, you can actually derive many related message passing algorithms or deep learning architectures. For instance, this is another one. You actually learn some embedding for each one is edges directly. So you are not just learning the embedding for edge, you are learning the embedding for each direction of the edges, okay? So for instance, this one approach, you're going to, for instance, represent the embedding for edge between H1 and H2, and especially from the direction of H1 pointing to H2. So in some sense, you want to capture some kind of topological information sort of on one side of this node of H1, okay? So in this case, then you can essentially also design a different propagation or message passing algorithm to compute the embedding. So in this case, you initialize each one is edge as some zero embedding. And then when you try to produce the embedding from particular node, I to j, in this case, example H1 to H2. So you're going to take this neighbor embedding from all other nodes except this destination node H2, okay? And do aggregation. So the difference in this particular case is in the update operation. So you are aggregating all these incoming messages from the neighbors except the destination j, okay? Except the destination j over there. And then you aggregate the corresponding node feature in a similar way, and then you push it through nonlinear operation, sigma function there. And then again, this update parameter W1, W2 is going to be some parameter learned later on using the supervision signal in the end, okay? So in this case, we typically run it into T steps. So we don't run it for infinitely long. And so in practice, actually, we just run it for 5 or 6 iterations. So very often this network is about actually 6 degrees of something like people are separated, six hops. Pretty much 6 hops you can reach everybody, right? So if you really want the convergent one, actually you can do that. One thing you can do is to make this transformation W1, W2 matrix, you restrict its singular value to be smaller than 1. So you can actually prove that even you iterate the infinite times, it's going to converge. Yeah. Okay. Yeah. Okay. Right. Yeah. So this one you can produce this embedding for the edges. In some sense, it's mostly looking at the topological information from one side. Information from one side of the network. Okay. And you can also aggregate this information to produce the embedding for nodes and for the subgraph as well. Once you have the embedding for each one of these edges, and you can also connect it to many downstream prediction problems. So I'm going to show you how do you actually apply this to dynamic graph analysis, some prediction problem or fraud detection problem in dynamic transaction graph. Okay. In this case, you want to actually capture graph information from just one side, not the other side, okay? So I'm going to talk about this example. Essentially, the simplest forms of this problem is people purchasing product on the online shops, yeah. So actually, it's a highly dynamic graph because at different point in time, people might buy different things. So each one of these transactions has a precise temporal information attached to it. And you might have additional context information about, for instance, rating comments for each one of these transactions. So previously, when people are dealing with this type of prediction problem, they might just use a matrix problem, more static, treating these as a static problem. So you will these transaction network as sparse matrix. And each row of this matrix is going to correspond to a user. Each column is going to be an item. And if this particular user have ever purchased a particular item, it's going to be some non-zero entries. Otherwise, it's 0. And you try to actually factorize or approximate this matrix by the product of the two-row matrix, U and V. And then once you have these U and V, you can make a prediction for every entry in this network and make a prediction, for instance, whether this particular person is going to like the particular product or whether this particular person buy the particular product is with high probability or not, could it be a fraud or not, things like this, okay? So, but we are going to actually make use of these temporal information. It's a very useful source of information. And the way we use it is by unrolling this dynamic network, okay? So what do I mean by unrolling? So for instance, this is a simple example. I have just 2 users and 1 shop over there. And then at a particular point in time, T1, these users go to that shop, okay? And then what I'm going to do is I'm going to create a duplicate node for the user and duplicate node for the user, the shop. I will have cross connection between the user and then the shop, and also this vertical connection between user and shops and shop. Sort of what the information I want to capture is because this interaction between the user and shop, I understand the user a little bit better because the user is defined by the type of things he buy, okay? And then the shop is defined by the set of people who interact with this shop. So sort of you want the information to propagate or across shops and user. Similarly, when there's a next transaction, right, and between the second user, Sophie, here with that particular shop, you're also going to create this duplicate node. You have cross connections and vertical connections. So you can imagine that the particular user may come back and buy and visit the same shop again. So you have a duplicated user again, and then also duplicate a particular shop. So you can see that in this graph, even this Sophie, this second user, never directly interacted with David, this first user. But because we have this cross connection between shops and users, information could propagate from one user to another user. If I understand one user better, I could understand another user better as well, okay? Via these shop connections. So you can imagine that the many shops in this Alibaba platform, many users, the network can get very complicated. And you want to actually learn some vector representation for each one of these users, okay? Such that you can make a prediction in future if you see a transaction, whether that's a normal transaction or not. It's normal or not, okay? So you can think about the graph, the abstracted graph is something like this, okay? The topology is exactly the same as this unrolled network. But each one of the user is going to have multiple nodes, like have some evolution of the user interests, okay? And each one is shop is going to have a chain upwards. It's going to capture the evolution of the shops feature as it progresses. So essentially what you want to do is, for each one is node, at any point in time, you want to learn some kind of embedding. Somehow capture this network down there, right? The historical transaction interaction of these users with shops and all this network down. So that's why you want to use these message passing algorithm, right? Just propagate this embedding from the historical transaction to the future node, right? So that's why you don't actually propagate information from future back to these historical nodes, okay? So you just do one direction propagation and trying to capture all this connectivity information in the past, and also some kind of transaction information acts here, okay? So with this, we actually applying it to this cache-out detection problem, okay? So in this case, you can think about the transaction that's happening in time, right? So it has a timestamp. In order for such a cache-out behavior to happen, in order for the money to flow back, so the temporal information is very important, right? you really need to have these account 1 somehow send something to account 2 in the past, and then the money flow back to account 1 at a particular point in time, okay? By this dynamic graph unrolling, we'll be able to see this type of thing, yeah, if you squeeze it as a static graph. So actually, it's hard to distinguish between these Fourier transaction, okay? So again, we compared these Structure2vec to some of these existing techniques already deployed in Alibaba, and it's doing much better in terms of detecting this cash-out behavior. As I mentioned earlier, every day is detecting thousands of more of these cash-out behaviors involving millions of dollars, okay? So it's very effective. Right, so I just want to give you a little bit more sort of intuition. What kind of thing could have been learned by this embedding, right? So we are doing much better in terms of accuracy, but is learning something that explainable, interpretable, or not, right? So I will use a slightly different example. Again, it's dynamic network for explaining what kind of things are potentially learned by this type of embedding, okay? So this is an example in some kind of event prediction. So I call it temporal knowledge graph prediction problem. So in this particular problem, each one is going to be some entity. For instance, President Trump, and it might be a city like Beijing, China, things like this. Okay, it might be Singapore, things like this. And then the relationship can be visits. Trump visits a particular country, and this country has some kind of cooperation with another country. This country, people here have some fight with other country, things like this. Okay, some kind of a political and international type of events. And you can imagine that the entity are going to correspond to people, place, and then the edge is going to correspond to something happened in the newspaper. So there's a gigantic data set called GDLT, and it actually has extracted many of these type of events from newspaper. It's going to be updated every day, right? So that's why this network is evolving. And you want to, for each one is node, for instance, President Trump might has involved in many, many events. You somehow want to capture the history of President Trump, right? Such that you can make a prediction that what could Trump do in future, for instance. Yeah, if Trump do something in future, it may be abnormal, okay? So again, we apply exactly the same network unrolling technique to this network, and learn embedding for each one is in entity in the network, capturing its historical interaction with the remaining of the network, and then make a prediction what could happen, okay? So it's much more accurate, but I want to pick out a few examples where this embedding approach is making accurate prediction, and then the sort of information capture seems to be making sense, okay? This is one example. In this particular example, the sort of event of focus is this middle one, Cairo. Some people from Cairo in 2015 has attacked some people from Croatia, because at that time, Cairo is involved in lots of social unrest. And then some tourist in Croatia is being attacked, okay, in that particular point in time. So, and this is a real world event happened. And then this Structure2vec approach is able to make a very accurate prediction for this thing to happen based on what has happened in the past, okay? So you can actually look at you can actually extract the corresponding network just before, okay, this event happened, okay? So essentially you can see that two paths from connecting Cairo to Croatia, okay? The top one and the bottom one. So the top one is like in 2015, earlier this year, March the 6th, and then some people from Cairo threatened some people from Manchester. And then later on, these people from Manchester also provide the help to people from Croatia. Okay, there's a positive path and a negative path over there. Okay, negative link. Okay, it's like enemies, friends. Okay, so the second path is very similar. In earlier this year, January 20th, Cairo people attacked some protesters, and these protesters also seek help from Croatia people. Okay, it's again enemies, friends. It looks like these two paths. Both are enemies, friends type of relationship. Sort of give you a stronger sort of prediction that there can be some conflict happening between Cairo and then Croatia. At that time, of course, this Cairo is also involved in many, many other fights, and then Croatia is quite friendly to other countries. Sort of all these evidence happened in the past enforces that something like this could happen. So our method is making a very accurate prediction, right? Okay, so it captures some kind of intuition, right? We understand daily, yeah. So the same, the same embedding approach and the same set of parameter is actually able to make prediction for other type of patterns as well. But this is another pattern, which this embedding approach is also making accurate prediction. Again, the event to focus is the middle one, where Columbia has some kind of cooperation with Ottawa in July the 2nd, and it's also predicted very accurately by these algorithms. So you also look at the network just before that. So you find that there's a top path there, and Columbia is involved some collaboration with New Delhi, and New Delhi involved some cooperation with Ottawa. And on the bottom path is like Columbia is reduced to some kind of cooperation relationship with Belgium. And then later on, Belgium is involved some trade fighting with Ottawa, okay? So there's a top path, friend, okay? And there's a bottom path, enemy. So both sort of, based on our data intuition, should strengthen the tie between Columbia and Ottawa. This embedding approach, which you summarize the history as of some vector, and is able to capture this type of data intuition. And even for the previous slides, it's a slightly different intuition we also can learn it. There are many other complex network patterns, temporal dynamic network patterns, is captured by this embedding approach and making very accurate prediction. But I'm just picking out this example to explain it. So this is something you can do with this embedding approach, summarizing the topological information and making predictions. And in the end, I want to talk about one application. How do you actually use reinforcement learning together with these deep learning over graphs to learn some kind of algorithms, okay? So this is a new application. Again, it based on this Structure2vec approach to capture some topological information. So for instance, there are many problems in combinatorial optimization problem over graphs. So one problem is maybe some fraudster, he has some fake news or some virus. He wants to spread in this social network, right? Some virus spreading or influence maximization type of problem. And then the fraudster may have some budget. Maybe he has $1 million. He can only infect 1 million people. Then he has to pick people carefully, right? And then such that to make sure that the impact is maximized, okay? Because because people are connected in this social network, if you find some nice people to infect, okay, so these nice people can help you spread, okay, this virus or fake news. So the simplest, the most abstract version of this problem is something called the minimum versus cover. So what is minimum versus cover? Essentially, you're given this network. What you want to do is to pick a small number of nodes as possible in this network, such that to make sure that every edge, okay, every friendship, at least one end, has been selected. Okay, this is a combinatorial optimization problem. You want to minimize the number of nodes you choose. So the more complicated version that the virus can spread to a larger population is called set cover. But the minimum versus cover is like you are only going to influence your neighbor, okay? So you want to pick a small number of nodes as possible, right? So this is a simple problem, but it's an NP-hard problem, right? So the attacker, if he wants to be efficient, he has to think about the algorithm to do it. And very often this type of problem is solved again and again, okay? It's not a single network the attacker trying to handle. So the social network, the topology is going to change all the time because sometimes two friends are not online simultaneously, right? You get one edge being removed, yeah? And then sometimes there's a new node being registered, then it's going to be some topological changes as well. So in some sense that you need to solve these a family of problems. They are more or less similar, but not exactly the same. So there's you can actually learn some algorithms which to be more effective in terms of picking the nodes. Okay, so previously, one of the very simple algorithm and used a lot is a greedy algorithm, and you also have a nice guarantee, two approximation guarantee. It means that if this algorithm is going to be around, the solution will never be two times worse than the optimal solution. Okay. The number of nodes you choose is not going to be 2 times more than the optimal solution. So these algorithms are particularly simple. So you just pick the nodes based on the degree of the node. Some very simple topological feature of the network. So you just look at this and know how connected it is to the neighbors. Okay? So if it's, the degree is high, you pick it. So in this particular two approximation algorithm, you pick the edge. You look at this edge. If 2n together, it has high degree, you're going to select it. Once you select it, you remove all the incident edges from network. You work with the remaining graph. Okay? And then you keep applying this until the entire graph is cleaning out. Okay? And then you can solve the problem. Okay? So, but what you might notice that in this two approximation algorithm, the criterion that is used to select a node is actually hand designed. It's a simple one based just on the degree, and we could potentially learn a better one. Okay, based on the topological information, how these nodes are connected to the neighbor, maybe neighbor 2 hops away. Okay, so we can actually learn some heuristics to do better than these two approximation algorithm. So essentially, you need a way to capture the topological information of this particular node in a network, hopefully summarizing as some vector such that you can define a scoring function for this particular node and use it to determine which node to pick. So that's exactly what we do for these Structure2vec. So in the high level, you can connect this greedy algorithm into a Markov decision process. Essentially, when you are actually using these heuristic to pick nodes sequentially, you are actually solving a Markov decision process problem. So you can, the top one is actually the formulation, the mathematical formulation of this minimum what is cover problem. So what you are going to do is, in this problem, each one is node is going to assign a binary flag of either 0 or 1. 1 means that that particular node is being selected. 0 means that it's not selected. So what you want to make sure is, for each one is an edge in a network, at least one end, for instance, ij is an edge. You want to make sure at least one end is being selected, such that xi plus xj is larger than or equal to 1. So you can think about that I can map this problem into Markov decision process problem. So the reward, every time you pick a node, you are being penalized by 1. You're getting a reward minus 1. Okay? So the current state of the problem is going to be the remaining graph you want to handle. When you want to take action, in this case, when you want to pick a node, you want to pick it according to some criterion, right? So that's called the action value function. How valuable is picking a particular node? So in greedy algorithm, you only look things locally. It doesn't consider long-term benefit of picking a particular node, right? And then once you have this scoring function, you just pick node greedily. You pick the node, remove the incident edges, you get updated states. Okay. So then we want to consider long-term benefit of picking some node. We want to learn some action value function, somehow take into more topological information in the network, and such that I can pick a node in the long run is also going to be very helpful. Okay, that's the idea. So what we're going to do is we are going to use this Structure2vec approach, which is ITV algorithm for extracting network features, right? And depending on the number of iterations you run, you look at larger and larger neighborhood. In the end, each one is node is going to have a vector representation summarizing the topological information. So this vector is computed based on parameterized update. You're going to use this vector to define your action value function, right? So you're going to compare this particular vector for a node you want to pick with the remaining network. Okay, that's why I'm drawing this function there, which has a bag, which aggregate all this embedding from the entire network and comparing to the embedding for individual node. So the particular parameterization can be something like this. You have these pooling aggregation over the embedding of the entire network, and then you compare it to the embedding of particular node I. So you have this additional parameter theta 1, 2, 3 there. You want to learn to score these particular nodes, how useful it is to the long-term reduction of these objective functions. And then together with these theta 1, 2, 3, you also have a parameter W1, W2 for these iterative updates. You will learn them together instead of learn them separately, okay? So you can learn it with something called the FDQ learning, standard in the traditional reinforcement learning literature. Once you finish learning this scoring function, okay, the parameter W1, in this update is going to learn, and theta 1, 2, 3 is going to learn. You can actually apply this embedding update to a new graph, okay? And then use these new graph. In this new graph, you can actually execute this greedy algorithm. So let me just in the end show you this video of comparison of different algorithms. The 3 panels are going to correspond to 3 different algorithms. And then the leftmost is going to be some kind of action value function, scoring function learned by Structure2vec. The middle one is going to be just pick a node based on the degree. And every time you pick a node, you remove the remaining edge, you work with the rest. And the last one is going to be edge greedy. Every time it picks a pair of nodes. So every time each one is going to execute one step, I'm going to produce 1 frame. Okay? For this edge greedy, because every time it's picking 2 nodes, I'm producing 2 frames. Okay? Every 2 frames, so 2 frames. Okay? So whichever algorithm finish the graph fastest is the fastest algorithm. Okay? So if you see one of these video empty out the graph fastest, is the best algorithm. Okay? So initially, it looks like the node greedy is actually pretty good, and edge greedy is also pretty good. And Structure2vec still get a very dense graph. But near the end, you will find that surprisingly, Structure2vec is actually the best one. Okay? It clear out the entire graph fastest. So the reason why this is happening is this node greedy and edge greedy is very local algorithm. It's not looking at the long-term benefit of choosing high-degree nodes. So then by picking this node greedily, so you're actually dividing the network into lots of small pieces. And they're not connected. And you are forced to pick at least 1 node for each one of these components in the end. That's why in the end it's slowing down. But these structures will sort of learn some kind of scoring function based on both the topological information, based on both the degree information, and also how useful this node for connecting the entire graph. So it's sort of balancing between the two. That's why even near the end, this Structure2vec has the potential to pick some node and reduce a large part of the network. It tries to keep the network connected. Okay, so that's what you see in this example, right? Okay, so in some sense, it discovers some kind of new algorithms. Yeah, more efficient these traditional algorithms. It can be used by these fraudsters to attack this network more effectively. Okay, we have to think about a way how to make it better. Okay, to prevent this type of thing to happen. If the fraudster get a chance to observe many of this network, and then he might be able to cook up some more efficient algorithms. In the end, I'd like to just summarize this. And essentially, what I presented today is something called Structure2vec, which helps you to take into account both topological information, connectivity information. So there's a complex network out there. Maybe the node type is different, edge type is different, there may be node feature. And then you also want to aggregate this temporal information and think about all this information together. Okay? Structure2vec essentially is some iterative kind of algorithm. You can think about some kind of recursive neural nets over the network. And this recursive neural nets, the recursive step is going to be parameterized. And the parameter is going to learn end-to-end with a final prediction task or a reinforcement task you care about. Okay? So in the end, it's able to produce state-of-art kind of results in various type of failure detection problem, and also learning some algorithms to do better. So with that, I would like to end the talk. If you're interested in working on this, so you can look into M Financial. We need more people to work on this problem. Okay, okay, thank you. Yeah.
Is there any questions for Professor Lasson?
Any more questions?
Oh.
So I wonder how you are solving that problem for the graph matching subproblem that you have.
Right.
Because you might have the known malware or the known problematic subgraph, and you are trying to look for the presence of a similar subgraph, but the control flow extraction there might be difficult because of indirect jumps.
Mm-hmm.
Maybe you can give us some feedback.
So you're asking this subgraph maybe embedding in a larger graph, or it's just noisy extraction? Okay. Yeah. Yeah. So in terms of the actual extraction algorithm, actually there's another expert here, Chang Liu, can give you an even better answer. But let me answer the part when you have a noisy graph after you finish extraction, right? So this type of approach, Structure2vec, is not looking for exact match.
Mm-hmm.
So it's actually looking for approximate match. So these ITV algorithms in the network is trying to somehow learn a way to compare graph.
Oh, I understand that, but it can be very incomplete. Means we have looked into this many times, but the graph extracted can be very incomplete. So I was wondering whether you have any thoughts or any heuristics that you are using.
Right. So one reason why we could do this good, it could be because we are using a more like a supervised learning approach to do it.
Okay.
So if you try to design some feature beforehand in an unsupervised way to compare it, then it's very hard to take into account that there may be missing part in one of these extraction graph, and there may be some additional noise in another graph. This learning approach sort of try to force you to get rid of those differences across platform in some sense.
Okay.
Yeah, so that's one reason that you could do better, right? So yeah. For instance, you have two graphs, right?
Sure.
One maybe have one more edge.
Okay.
So the learning process can sort of help you sort of learn the pattern that particular edge is not important. Right?
Okay.
That's potential benefit of
I
supervision.
sort of buy that.
Yeah.
The other thing, the small comment I have is about that friend and enemy example that you gave.
Right.
So it's quite well known that both at interpersonal level and at nation state level, the friendship and the enemy relationship is very one-to-one. So it's very common to have X and Y fighting among each other, and Z can be friends with both X and Y, either at a personal level or even at a nation state level, without giving any concrete examples. So in this case for Y, Z would be enemy's friend.
Mm-hmm.
So I wonder whether your deep learning system is doing a very simplistic kind of deduction. And is that because you trained it to, you kind of provided these kind of rules in some way, or it just came up with it on its own?
It just came up with it. So
From
essentially, right, that's right.
yeah.
So some of this common sense just came up by the learning. So essentially, what is learned in this process is just some parameter updated.
Okay.
And in the end, you actually, what is learned essentially is some vector representation of the history, actually.
Okay.
That's a common problem of deep learning, which needs to be studied more, is how to understand this embedding.
Sure.
But in the end, the prediction is very accurate. Look back, it seems like it's capturing this type of common sense.
Okay.
Right. It's also capturing some very complicated pattern. I can't even understand it. Right.
Sure.
And but these are some examples which somehow easy.
Okay, thank you. But that's not how human relationship works. So I think the deep learning system is still making a simplistic deduction.
Right. That's right. Yeah. Okay.
Thank you very much. I think for time constraint, if you have further questions, we encourage you to approach Professor Song after this.
Okay. Thank you very much for listening.